have suppose two solids. So we are writing 1 and 2. Atkins is writing the components as A plus B. That is just the same. Okay. And remember that suppose we have two solvents, right? And suppose, for example, the mole fraction. Okay. If I just plot the mole fraction of the component A, okay, which means the mole fraction of the component is plotted like this for B, right? When this is 0, xB is 1, okay, and when xA is 1, xB is 0, something like that, okay. So when xA is 0, it will be basically PB star, vapor pressure of the pure solvent of B, okay. And when xA is equal to 1, I will have PA star, okay. Similarly, when so this will be basically the total variation, okay, for the two solvents, but individually, so you can understand that this will be something like this, okay, if one component was present, okay, and the other one will be something like this, and this is the ideal behavior, okay. Now when you talk about solute solvent, okay, we only talked about solvents activity, in the sense like A is suppose present in large excess when it is pure, okay, so it will approach this line, right? That is Raoult's law. But then the question was, okay, fine, if I plot it for a real system, as I told you that when XA goes to 1, right, for the pure system, then actually the curves actually coincide, right? But there is a huge deviation at the early stage, right? And it makes sense because actually these two points should match, okay? But here the deviation is more because XA is less, right? Clear? Now, suppose a different situation, in the sense like, let me actually call this as XB, in the sense that I'm calling A as the solvent, okay, and B as the, say, solute. So I just reverse the curve, okay, so this is basically PB star, okay. Let's think in terms of B, okay. This is basically the, like, variation of the vapor pressure, okay, with mole fraction for B. Now, when B is present in less amount, then actually we call it as solute, right? There are some solids which are involatile, which by definition is solute, but suppose I am actually mixing two solvents, let's say acetone and chloroform, that's a standard example, okay. Now, when acetone is less, chloroform is in large excess, then you call chloroform as the solvent, acetone as the solute. But if the situation is reversed, that is that the solute and solvent concept is reversed, okay. Now, XB, usually we call it as a solute, okay, when XB is close to 0. Now you think in the other way. For that situation, okay, if this is the ideal curve, as you see that when XB is close to 0, okay, so things do not actually like match, right? And then empirically there is a law, it's called Henry's law, right? So it will be basically a slope like this. If I draw it in a better way. Where's the duster? Okay. So what Henry's law says is that if I actually take the limit when XB tends to 0, okay, then I have a situation which is known as dilute solution. Okay, what I am saying here, this is actually ideal behavior, which is the Raoult's law, right? Raoult's law, strictly speaking, is valid when the solvent is in the pure form, right? Now, when we call it as a solvent, when it is in the large excess, like when it is approaching 1, right? But on the other limit, okay, when actually that is in a very less amount, right? So then there is a huge departure. Meaning, if XB actually acts as a solute, there is a huge departure. And to describe that, basically Henry empirically said that, okay, fine, let us consider the similar thing. Okay, similar thing in the sense that here, when xb tends to 0, the vapor pressure, okay, or PV will be proportional to, of course, mole fraction. Okay, but this proportionality constant is not PV star, because as I see that it cannot be, say, PV star into xb. Why? Because when xb is equal to 1, okay, this is PV star, but actually the slope actually is showing this is something else, right? So he empirically said that, okay, this is some other constant which we write it as Kb, which is known as the like Henry's law constant, okay, which is different as from the basically P star. Clear? Okay. But again, these are all empirical things, because I'm assuming that if it behaves, okay, ideally for all concentration range, meaning the PV is varying with xb, okay, the vapor pressure of the solute means when I started from a lower concentration, is varying as a mole fraction, okay, and the proportionality constant is Kb, then I'll have this line. So this line is actually an ideal behavior, but this is for ideal dilute solution, because it usually is valid for xb tends to 0. And this line we call as the ideal behavior, Raoult's law. That's why Henry's law, people write it as an ideal dilute solution. All the straight lines are ideal behavior. Why straight lines? Because actually it is linearly varying with mole fraction. But when it is approaching pure solvent, then actually it is merging the real, this is the real curve basically in between. Okay, the real curve actually will merge the Raoult's law when thus basically the mole fraction is going to 1. That's why people say that Raoult's law is valid for solvent, and Henry's law is actually valid for the other limit, where the initial thing of the real curve merges with that other straight line, where when xb goes to 0, which means actually xb is behaving as a solvent. So basically Raoult's law and Henry's law are both empirical, and both are proportional to the mole fraction. Constants are different. Okay, and the second thing is that it is your perspective, how do you look at it? In the sense, like I could have like drawn a like real curve for these two together. Okay, then in one limit one becomes solvent, in the other limit the other becomes solvent. Okay, and the solute solvent notations are different. Now the reason I wanted to introduce this thing, already you know all this thing, is that this simple thing doesn't hold if I use electrolytes. Okay, so because electrolytes are generally solutes. Okay, and so what I'm saying here, already you know this thing, the activity we define, okay, as basically P by P star. Earlier case we were using 1 notation, I'm just using A notation right now, okay, instead of 1, and I'll use B notation instead of 2. Okay, alright, but A and B again are just your choice. Okay, like what is solute in your definition can be solvent in the other limit. Okay, alright, and already we know that if the mole fraction tends to 1, right, then actually this thing will tends to this, and AA by definition we actually like said that it is proportional to the mole fraction through a proportionality constant that we call as a gamma, which is activity coefficient, right? Now the similar thing we can also write for the solute, which means similar thing we can also write it for B, okay, when B is in less amount mostly. Okay, because in that sense, the remember this thing, like when XA tends to 1, these things are valid mostly, right? The activity is basically approaching XA, as well as this gamma activity coefficient is also approaching 1, right? Now I'll have basically the opposite situation if I write it for B. Again, don't get confused. The same thing can be valid for A if A is in the other limit. Okay, A and B are just arbitrary. Okay, all right. So if I just use the similar notation, okay, for the B. Now look at it for B also. I can write it the chemical potential as mu B star plus RT ln PB by PB star, and this is exact. Okay. For solvents, we actually wrote this as XA. Okay. Solvents we are using A. If actually B is solvent, I will write it as XB. But right now I am considering B is solute, meaning B is the component which is less. Okay, as simple as that. Now the problem here is that this is not actually, if I write it as a XB, that will be actually Raoult's law. Okay, but I have to use actually Henry's law, which says the PB is basically KB into XB. But KB is an empirical constant. Clear? The other straight line. Okay. So basically there are two straight lines. Okay, the real curve actually marches with this straight line when mole fraction is less. It marches with the other straight line when the mole fraction is more. Okay, which means that is more solvent-like and this is more solute-like. I am now looking at or casting the problem entirely from the solids perspective. Okay. Now this is correct up to this point. Now I can actually write it. Look at it. PB mu B star. Okay. Now what I will write here instead of PB. Okay, I can write KB into XB, right? And then I'll just write it like this: KB into XB. This KB by PB star, that I'm writing separately. Okay, and the XB I'll just write separately. Clear? Okay. Now think about it. This thing. Look at the Raoult's law thing. If I had written it as a Raoult's law for A, okay, how do I write it? I write mu A is mu A star plus RT ln XA, right? I want to write a similar thing. So I'll just write it as something like this is mu B0, kind of a standard potential, this entire thing, plus RT ln XB. Clear? Okay, and this is, if this is valid for all the concentration, okay, then this is called Henry's law. That this is basically the Henry's law version for the solvent. Okay, but again, it doesn't vary for all. It will not be true for all concentration. So what I should write is that if B acts as a solvent, okay, then I should have written it as a mu B star plus RT ln XB. This is actually Raoult's law. Right? Okay. But condition is that this is valid for all concentration, then only Raoult's law is valid, which is this line. Okay. But actually it doesn't. It only is valid when XB tends to 1. We discussed it. Right now I am saying the other limit. Okay, I am saying if this is valid for all concentration or all mole fraction XB, then it is Henry's law. Okay, but actually in reality it is valid only when XB tends to 0 on the other limit. Okay, but the only thing to point out here is that the standard state definition is slightly different. It's not exactly the mu B star. Clear? It makes sense. Why? Because how do you define the standard state? Let's say when XB is equal to 1. Okay, what I will have? I will basically have this term will vanish. Okay, now XB is equal to 1 means PB and KB are equal, right? Which means actually this is 1, so this term will vanish, so mu B is equal to mu B star. Makes sense. Okay, so if I had started with a pure solid, 100% pure solid, okay, then mu B will be equal to mu B star. So this is an effective standard state, which actually takes into account of not only mu B star but also the other constants. Clear? Okay. Now, in practice, okay, whenever people write for solids, people do not use this equation. Why? Because people usually do not try to avoid everything to write in terms of mole fraction, but rather they use molality. Okay. Now, again, you can write any equation in the sense that you can actually define the activity also from this thing. Let me first define the activity for B. Okay. So this is from a solvent perspective, and this is for a solute perspective, right? Again, this is an approximation. I should have written it here. Because I'm replacing this thing, PB by PB star. Okay. Basically, PB as KB into XB, that's an approximation. Because that is valid only for XB tends to 0. Okay. And from the solid's perspective, we always write it in this way. Okay, strictly speaking, this is valid in the limit when XB tends to 1, and this is valid strictly in the limit when XB tends to 0. Usually, textbooks actually write, whenever they write this equation, they write in terms of A. And whenever they write this equation, they write in terms of B. But what is A actually can become B. I mean, the solid. Okay, so that always keep that in mind. Okay. Now, the similar way we defined activity. Okay, we said that okay, fine for real solution. Okay, it will not be mole fraction; it will be just activity. Okay, and then we made a connection. But we yesterday said that there is no surprise of the activity of like the solvent, right? Because it is directly defined as PB by PB star. Because up to this point, remember the equation is exact. Okay. Similarly, I can also define the activity for the solute. Okay. So how do you define it? Activity for the solute. See, it will not be now PB by PB star. Okay. So it will be basically PB by KB. Okay. Now, why it is PB by KB? Anyone? Why I am writing it not PA by PA star or PB by PB star for this thing? See, what I am saying here is that I can write this equation, okay, as mu a 0, okay, plus RT ln AB. That is an exact equation. Okay, this is an approximate equation. Why approximate? Because I have written here Henry's law. Okay, and even if I plot it versus XB, I know that's a straight line, but that straight line matches when XB tends to 0. The other straight line. Okay, and this straight line is for Raoult's law, which is the lower straight line. Okay, the way I draw it. Okay, and that is valid when XB tends to 1. Okay, actually everything is like a real solution. Okay, now I said that okay, for real solution, I will replace this equation as mu B star plus RT ln A, right? And then I compared this thing with this thing, and I got actually A definition is PB by PB star. Clear? Now, similar way, I can also define that okay, so this is not actually an exact thing, okay, but I could have actually got an exact thing, something like mu B star plus RT ln activity of B. Now you just compare this with this, you can easily figure out the activity has to be PB by KB. Just check it, like if I write it as PB by KB, okay, then what it will be? It will be PB by KB. Okay, I can combine these two things. It will be PB by PB star, which is exact. Clear? But it is not coming as PB by PB star. Why? Because I defined this as the standard state. That's why the KB actually one extra term is coming out. Clear? Okay. It is just like notation how you define the standard state. Because I am looking at now everything from the solid's perspective. Okay. Now this is exact. Okay. This is an approximate thing. Okay. Exact with the approximate, can I actually write this exact term and connect it to the approximate? Again, it's the same thing, like I'll write AB as if it is proportional to XB or effective mole fraction, and then I can write the activity in terms of the activity coefficient times the mole fraction. Same one. Okay. So meaning I can actually just write, I wrote this equation. Okay. Assuming that this is always for the approximate thing, but the real thing, which is the activity, okay, which describes the real solution for all condition, okay, can be thought of as something like X proportional to the mole fraction, okay, and the proportionality constant is gamma. But then gamma actually is not simply just a number, because it is accounting for all the real thing. You know that the curve is very much nonlinear. Okay, so gamma is a function of X actually. Okay, always, because if it is just a number, then again it's the same problem. It will be a straight line. That cannot be true. Okay, so the real challenge or real charm is now everything is sitting inside the gamma. Okay, gamma is the nonlinear function. Similarly, here also I can write xb, AB is proportional to xb, or something like AB is gamma B into xb, where gamma B is basically activity coefficient for the solute. Clear? Okay, notations are just parallel, but only thing be careful is that this is PV by KB and that was PV by PV star. Okay. Alright. Now this is one way of defining the activity. Okay, but you are free to actually write this equation anyway, in the sense that suppose I do not want to write this activity. Okay. I don't want to write it in terms of activity. I can write it in terms of mole fraction. Okay. Meaning the same equation, I can actually write it. Okay, I will not use this equation, and rather like write something like it is mu b 0 plus RT ln b by b0, where b is basically the mole fraction of capital P. Sorry, molality of capital P. Okay. Now, when you write it, okay, when you read Atkins, this is a very confusing thing. Then these two mu zeros are different. This is just a equation I am writing so that this just is valid. Okay, I am assuming that okay, fine, everything will have a variation with instead of a mole fraction, everything will have a variation with molality, right? I can write the concentration in terms of mole fraction, I can write it molality, I can write molarity, whatever. Okay, useful thing is usually molality for solids. Okay, so Atkins has written this equation. Okay, but these mu b0 and these mu b0s are different because there is no comparison, you can see, right? So this mu b0 must be very different. This is an empirical thing. So let us not like discuss anything about it. But the point here is that you can write everything, okay, in terms of just the amount. Okay, like in any case, like activity or mole fraction, molality or whatever you write. Okay, you just add the amount and then you talk about it, and you can approximate everything in terms of say a proportionality constant, which is basically activity coefficient for the solute. Okay. Problem is now if you look at the curves, okay, I showed that when the solute actually goes to 0, meaning when it is a dilute solution, right, then it behaves ideally. So there are two ideal curves, remember, okay, and there is an ideal dilute solution. That concept is there. Now how dilute is the dilute? That's a good question. Okay. Now say when you look at the real plots, you will see like when the mole fraction is say, let's say 0.1 or less than 0.1. Now less than 0.1 means what? 1/10. Okay, like 10% of the solute is present. Okay, and 90% is the solvent. Now just take a number. Like say for example, I take salt in water. Okay, pure water. If you take, what is the molarity of pure water? It's 55 mole per liter. Okay, pure water. You just take the weight, divide by the molecular, you will get this number. Okay, like on the order of say pure 10 like moles per liter of a solvent, right? Now which means if I have a 1 mole of solute added to it roughly, okay, so that is 0.1 mole fraction will create for the solute. Okay, okay, 1 mole means actually it's a 1 molar solution. It's actually two considered solution. If you add 1 molar, okay, solution of sodium chloride now to water, and if you think that okay, things will be similar because it's already an ideal dilute solution, it will never be ideally. Okay, the reason is for electrolytes, okay, which have actually charged species, they show ideal behavior much lower concentration, not actually 1 molar, it shows at least a millimolar or even less. Okay, why? Because now everything is charged. Okay, and all this, Henry's law is not valid. So long story short, what I am saying here is that I had Henry's law, this is ideal thing, okay, and that was basically, there was a range where the real curve matches with the ideal thing, okay, in the limit when the mole fraction is very small. That's why I call it, and this curve is for ideal dilute solution, right? From the perspective of the solute, okay, And then I said that the mole fraction will be something like, let's say, less than 0.1. Okay. But if you had done it, not with acetone, benzene or all these things, okay, acetone chloroform mixture, something like that. If this was actually sodium chloride and water, okay, this thing will be very, very different, the real curve, okay. And actually it will show like real kind of behavior in a very, very small range, which is something like less than 10 to the power minus 3 molar kind of thing. 0.1 mole fraction means actually it is roughly like 1 molar solution. That's what we calculated, right? Because the solvent is usually 10 moles per liter. Okay. Now see, there is a huge change in the order of magnitude. Okay. Which is arising because of the specific nature of ions, that ions are strongly like interacting with the solvent, and that interaction you cannot ignore even for an ideal solution, even for a dilute solution. So, okay. Now the question is how to tackle that problem. Okay. So we have to do the similar way. We have to define an activity. Okay. We have to define an activity coefficient. Okay. And we can empirically get an equation. Okay. But can we actually do and like this empirical constant, like say Kb is an empirical constant, for example. Okay. Can we actually solve this in an analytical way? Okay. And then basically two scientists who are very, very well known, Peter Debye and Eric Huckel, basically took challenge to solve this problem. Okay. And they basically came up with a theory which is known as the Debye-Huckel theory. Okay. But before we go to the Debye-Huckel theory, let me first just tell you, okay, how will you write first formally the activity coefficient for ions or in ionic solution. Again, from now onward we are thinking in terms of say solute, meaning the ions which are present are very, very small quantities. Okay. And again, ionic solutions show ideal behavior in a very, very dilute limit, like 10 to the power minus 3 molar or so. Okay. And the challenge is why a little bit concentrated solution shows so much departure. So there must be something, which means that Henry's law, the empirical constant, which is Kb, okay, is strictly valid for non-ionic solution. And all our duty is now left with for ionic solution. But it is very important to know because that interaction controls like many things. Okay, in biology, in chemistry, everything, ionic activity, right? Now, before I start that, just like I wrote an empirical way, like I said that I can write, I have a chemical potential and that is varying, and there will be something like RTL and something here. Now I define this as activity. I said that I could have written it as ratio of the molality. Okay, just basically standard molality, which means what is the unit? 1 kilogram per 1 mole per 100,000 kilogram or something. So that is basically to make it unitless. Okay. For a solution which has say protons, okay, many people actually use the concentration of or activity of the H plus, meaning you can actually write in terms of the pH. But then every time you write it, the mu zeros will be different mu zeros. Okay, all the mu zeros are not same because that is defined as when pH will be 7, then it will be the standard state. Okay, your gas phase mu zero was defined when actually it is 1 bar atmospheric pressure, right? So those standard states are different. Okay, so all these mu zeros will be different, but it is your choice. You are varying something like suppose I am varying pH and looking at the activity of something, okay, of an ionic reaction where proton is present, okay, something like that. So you can actually write this chemical potential in any language, okay. The variable is your choice, whether you are using mole fraction or molality or pH, it is your choice, okay. But the corresponding standard states will also change. Clear? Alright, actually Atkins has a discussion on like biological activity, where he has written this in terms of activity or the concentration of H plus. Okay. Now, so what I was saying is that I have suppose a Gibbs free energy, okay, for the ionic solution. Now when I am saying ionic solution, the ions are basically solid. They are present in less anion. So by definition they are solids. Now the molar Gibbs free energy, that will of course will have something like I can actually write it as basically the free energy for the cations and the free energy for the anions, because energy is additive, as simple as that. Okay. Now mu plus I will just write for cations, mu minus is for anions. So the Gibbs free energy is basically additive. Okay. Now the idea is that if they behave ideally, okay, I can use the cations as ideally, anions as ideally, and if I just add it, I'll get an addition of the total Gibbs free energy, okay, which is basically behaving ideally. Okay. Again, this is basically what we wrote as mu b, the solid. But the solid now dissociates into cations and anions. As simple as that. Okay. Every step, if you do not understand anything, please let me know. Okay. Alright. Now what I am writing is that fine. Exactly the similar approach. I can write for the real solution. I am not writing real here. If I write G bar, it makes the sense that it is just a real. Okay. For ideal thing, I will just write ideal. Okay. So that is again the sum of the cation and the anion. Okay. And that I can always define something like the ideal thing and then some activity coefficient, because we know that what was the difference between the real and the ideal thing. Mu minus mu ideal was basically ideal in terms of the activity coefficient. Okay. So that way I am just writing it as something like, say, G bar ideal, okay, plus, or maybe just write one more step. So what I write it as mu plus is nothing but mu plus ideal plus RT-ln some gamma for the cation. Okay. Similarly for mu minus, I will just write mu minus ideal plus RT-ln some gamma for the anion, because cations and anions will have different activities. Makes sense, because the sodium ion interacting with water, and that interaction will be very different, like chloride ions interacting with water. Okay, for the solid being sodium chloride and the solvent being water. Clear? Alright, so these mu ideals are nothing but my original like G bar ideal, right? And so I see that there is basically two terms, okay, RT-ln gamma plus and RT-ln gamma minus. Okay. Now the question is, okay, so for every electrolyte, then I have to define two activity coefficients, which is very difficult to handle. Okay. So people said, look, I mean, this is just an empirical thing, okay, which I am assuming it to be real, but of course I have to find the activity coefficient so that it behaves really as a real solution. Okay. But instead of writing two constants, I could have written a single constant. Okay. Meaning, I am talking about not the activity of a cation or activity of an anion, some mean activity of cation and anion. Okay. And that I am writing as something like gamma plus minus. Okay. You have seen this thing, right? And that I am defining it as gamma plus, gamma minus to the power half. Okay. Now, this half is coming, okay, because actually I took like it's a 1-to-1 charge like sodium chloride. Okay. But we can actually derive a general expression. General expression in the sense, suppose the cation is the salt is something like, say, has the formula of this. Okay, meaning I have M is the cation, I have P. Okay, cations, and X is the anion, Q is the charge. Then actually we can actually derive all these things. Okay. Now before going back to I mean for a single gamma plus minus, okay, I want to replace it, okay, by gamma plus minus. So what will be the relation? Okay, so if I just want to go switch from here to here, so you can think that there is basically gamma plus into gamma minus, right? And then it will be square of that, right? Gamma plus minus. That square basically you can think 2 RT-ln gamma plus minus. Now that 2 factor, I am saying as if one goes to cation, one goes to anion. In the sense, what I am trying to say here is that this mu plus thing, okay, now I should have written as mu plus ideal plus one combination of this thing, RT-ln gamma plus minus, okay, and similarly the anion, I am just writing mu minus ideal plus RT-ln ln gamma plus minus. If you add these two things, you will get back your original definition. Okay. Now what did you do actually? We said that there is a deviation. Okay, deviation from ideal behavior. But the deviation for the cation and for the anion is basically same. Meaning the cation and the anion is behaving similarly. Okay, which is a big approximation. However, we'll see, of course, I mean, that is the approximation in the theory. Because you can think that the cations and anions might have very different like sizes, and they can have very different polarizabilities, right? So, but that's a molecular picture very much. At this point, we are saying the cation's polarizability for the solvent and anion's polarizability are same. Only thing is that there is a stoichiometric difference. Okay, but the activity wise, okay, they are just same, and that I can always define as a mean activity coefficient. I can always define that, but then my task is that what is the expression for this mean ionic activity coefficient? Because everything is now hiding here. Okay, the ideal part, by the way, when I am writing the ideal means actually it's just whatever we showed so far. Okay, like the Henry's law, which means actually when charges are absent, like cations are there, but as if they're just particles, but there is no charge. Okay, so everything in that gamma plus minus, if you want to think very conceptually, you have to think like what is the effect of charge. Okay, if I add charges on the solute, what will come out? Clear? Okay, so that's how we'll basically approach. Okay, now again, we could have actually written it as MPXQ that way, okay, but it is again the same thing. And then what we just make a notation is that the total S is what? S is basically the total number of cations and anions, because see, that will be reflected after all, because the cations and the anions have the similar activity coefficient. Okay, it's a mean activity coefficient. Mean activity coefficient. Okay, and so then the total number of charges will be basically S, which is P plus Q. Okay, total number of ions present per mole. Actually, if I have to multiply by Avogadro number, as simple as that. Now, Debye came up with a theory where they actually gave an expression for this gamma plus minus, because that's what we need. Okay, because if I know the gamma plus minus, the activity coefficient, I know how it is deviating from ideality. Okay, ideal behavior, because the ideal thing we already know. Clear? Now they said, okay, so that we are going to see how they basically say. Let me first write it. Okay, I'm just writing the same notation. You have seen it earlier. Okay. Okay. So what is this? They said that if I take the logarithm of the mean ionic activity, right, and then it is some constant A times Z plus is the charge of the cation, okay, Z minus is the charge of the anion, okay, and this is a modulus of it. Why? Because suppose if I have sodium chloride, it will be just 1:1, because the charges when they multiply, there is already a minus sign that I have already taken out. Okay, and then there is something called ionic strength, already you know, right? And the ionic strength is defined as half sum over. Usually we used to write mu I n I square, but here actually the Atkins notation is writing as Zi square, okay, Bi by Bz, okay, where Bi is basically the molality, okay, but ionic strength is a unitless thing, right? So that's why I'm dividing it by basically the unit of molality, and Zi is, I have to take basically summation over Zi square, and I here is basically two species, one is cation, one is anion. Clear? Okay, so there will be two sums. Like for example, if I take magnesium sulfate, for example, okay, MgSO4, so you can easily calculate it, right? Or say Na2SO4, something like that. Okay, so then actually Z will be accordingly, right? So you have to take basically two factor here, because you know all these things like sodium sulfate, right? because the molality will be twice. When if I take one molar thing, right, it will dissociate into like basically every Na2SO4 will give 2 of sodium, 2 molar sodium and 1 sulfate, right? So I'll have 2 here, but it will have 1 square. But for the sulfate, it will be 2 square and 1 equivalent of this. Okay. And that's how we calculate. And this formula is very well known to you. Okay. Question is, what is A? Okay, that's a constant. But this is not an empirical constant. This is an analytically derivable constant that Debye and Huckel did. Now, before this thing, Peter Debye did lot of work on electrostatics, you know, right? And he had like monumental work on dipole moments of molecules, right? Basically, what gives rise to intermolecular forces, which we will study at some point in this course of electrostatics of molecules. And Eric Huckel is the same Huckel who gave basically the Huckel molecular orbital. Okay, and it was, as far as I know, it was the Huckel molecular orbital era. Okay, it is around 1930s or so. Okay, and 1935 probably Huckel gave the Huckel molecular orbital, but I may be wrong anyway. So in the Debye-Huckel description, what they said is that, okay, fine, let us just think about a very pictorially. Okay, as if I have some ions. Okay, and these ions are basically randomly moving around in the solution, whatever. Okay. Now this is kind of a snapshot. Okay. Now they said, think about one situation, like if I start from a cation, okay, and if I just go outside and then if I just take a fixed length and just take a sphere, okay, I'll encounter many cations and many anions, of course. Okay. This is a snapshot in the sense that in the next minute everything will be changed because they're moving around. Okay. But they said that on average, the number of cations entering the sphere, number of anions leaving the sphere will be same. And not only that, if I actually take a sphere, okay, of some fixed length, okay, on average, I should encounter one excess anion around the cation because the solution has to be electrically neutral. Something like that. Okay. Or if it has something like M, Q and that kind of formula, okay. So I'll have similar number of, like say, if I have, let's say Na2SO4, okay. So like, if I consider one sodium ion, how many sulfates are there in that particular sphere, okay. Then it is half of the sulfate ion on statistical basis. If you actually look at one sulfate ion at the center, take a sphere, okay, a larger sphere, of course there will be many, but statistically there will be 2 excess sodium ion around it because it is Na2SO4, something like that. Okay. Now that thing is basically, they said, I can actually think about it as a kind of continuum, although I will just calculate the number of ions in it because these are discrete spaces. Okay. And they said this is, I will call it as some kind of local atmosphere, and they told it as this is known as ionic atmosphere. Okay. Now this is a very pictorial thing. Okay, so I have the ionic atmosphere, and now what the activity is coming from? The activity is coming from this ionic atmosphere is creating a potential. Okay, all I have to do is basically calculate. Okay, before we go to that, what is the physical interpretation of Gibbs free energy? Gibbs free energy actually is a kind of, you can say, non-PV work, right? Now the non-PV work means here also we are talking about non-PV work because it's a solution, right? It's not expanding, there is no pressure volume work. All the work is basically electrical work, okay? Where we wrote, as remember at the very beginning, in the thermodynamics, the first law, we said that every time we are writing that D cross W term as minus P opposing dV, only for PV work, then can be non-PV works also, okay? Now we can say that the change in Gibbs free energy is basically related to the non-PV work. So all we have to calculate is basically what is the electrostatic work done, okay? Because you can think that there is an electrostatic potential, and then if I multiply by the charge, I will get basically the energy stored in the system, which is roughly the work done, okay, due to the presence of the ions. Secondly, this work done, or this will basically increase the activity, okay, or the chemical potential, I mean reduce the chemical potential basically. Why? Because as you can see, there is a attractive force always, okay, because it's a cation anion and they are getting stabilized, so there is something extra we are having on top of Gibbs free energy of mixing and other things. But the mixing and everything, I already told, these are the mu plus ideal, mu minus ideal. That we are not going to write. All we are going to write is the non-ideal part. Because the non-ideal part is directly connected to the gamma, but I defined a new gamma which is gamma plus minus. Clear? Okay, which is the mean ionic activity. Alright, now the question is, this is known as Debye-Luckel limiting law. In the sense like, it is also valid for the lower part of the concentration. Okay, although it correctly matched like few up, I mean above few millimolars, but not up to say 1 mole. 1 mole is a too strong ionic strength. Okay, clear. So there actually you see departure because there are a lot of like assumptions here. Okay, now let us just try to understand like how Debye and Luckel approach this problem. Okay. Now all I said is that I have to somehow calculate the work done. Okay. Now what is work done again? Work done again is related to the Gibbs free energy, right? This is actually non-PV work. In this sense, I am writing it as an electrical work done. Okay. Now electrical work done, okay, will be basically the chemical potential. Like okay, so think about it. Like I have cations and anions. Okay. Now how many cations I have? I will note a formula here. It is MPXQ, right? So I have P cations and Q anions. Okay. I have basically P moles of cation and Q moles of anions, something like that. Okay. All the expressions which I am writing is for 1 mole. Clear? Okay. Now, how do you think like there will be the electrical work done? The electrical work done will be the total work done minus, I can think, the ideal work done. Because that is the non-ideality and that is the origin of the electrical work, right? So what I am trying to say here is that there will be a total thing, which means there will be something like mu plus, which is the work done, but mu plus is for something like NaCl, mu plus or plus mu minus, okay? But here suppose I have P cations and N anions, okay? So the total work will be P times mu, Q times mu minus, right? That is the work done. Because everything is energy, right? Gibbs free energy is related to the work done. That is the total thing. But again, in the total thing, there is an ideal and non-ideal contribution. So I have to basically subtract the ideal contribution. Then only I will get the electrical work. Because there is also a mixing part. Okay, that is a purely like statistical mixing. Okay, the Gibbs free energy is also changing due to that. But that will happen even for electrically neutral spaces. That I don't want to calculate. So I have to just subtract from it this thing. Clear? Okay. And then I can always rewrite it. Something like this is nothing but mu plus minus mu plus ideal. Okay. Plus I'm just writing the cations together and anions together. Mu minus minus mu minus ideal. Okay. And then this thing, as you can see that we have already written it. Remember what we wrote? For mu plus we wrote that it is mu plus ideal plus RT-ln gamma plus minus. Remember? Okay. So what I will have, okay, here is P. For the Q also it was same because I said that it is mean ionic activity. Okay. So I can just write it as a Q RT-ln gamma plus minus. Okay. And P and Q, it is together I am writing as S. Okay. This S RT-ln gamma plus minus. Okay. So whatever is this RT or ln gamma plus minus, okay, that will be something like work done WE, right, divided by P plus Q into RT. P plus Q I am just writing as S RT. Okay, when I was reading it, okay, Sachin Ramesh Tendulkar. SRT is coming. Okay. Anyway, so now this is still like I have a formula for ln gamma plus minus, but what is the work done? Okay, I just said the work done is the difference of the chemical potentials, right? But I have to calculate it from that model, which model I actually showed you. Okay. Now here's the challenge. Like how will I do basically the work done? Okay. Now let us do very step by step. Okay. Now think about it. All of you know about basics of electrostatics, right? Like how the Coulomb potential varies for an ion. I'm just using the same notation here. Suppose potential, okay, due to charge I, it can be cation, it can be only two species are there. Okay. So that already I know that it is something like charge of the species, right? Times E is basically the fundamental charge. 4 pi epsilon, and then there is R. I'm just writing it like this. Okay, so this is a constant times R. So Atkins has written it as Z. I may use it as say some constant C. Okay. Now this epsilon is the permittivity, which means actually this is nothing but epsilon 0 vacuum permittivity times the relative permittivity. Okay, clear. Now this is for a purely Coulomb potential. Okay. Now Debye and Buchel said, okay, for a charged atmosphere, you can show it, I mean, we'll show it later. Okay. This variation will be more rapid in the sense, like, suppose I have a charged cloud, right? Remember what is the picture? Like, there is a cation, and suppose cation is also moving. Suppose that is your central cation, and suppose you are sitting on the cation. Okay, so there is no relative motion for the cation. Now you are seeing everything else around it is also moving. Okay, so you will see a diffuse charge cloud, the ionic atmosphere. Okay. Now, if I actually now move along this diffuse ionic atmosphere, you will see for a charged cloud interacting with a point charge, okay, the potential will not vary like this because this is between two point charges. Okay, it will be slightly modified, and which means it will actually decay more rapidly. Okay, so for a diffuse cloud, so this is for a point charge with point charge. Okay. This will be something like the same expression, okay, like some constant 1 by r, but there will be something like it will also vary as t to the power minus r. Okay, but of course there should be some characteristic distance because this should be dimensionless. Okay, and that characteristic constant is of course a dimension of length, which they call as Debye length. But up to this point, this is basically the interaction potential for a ionic atmosphere. Which ionic atmosphere? Which is I showed. Okay. So this is how the potential is changing. Okay, clear? Now all I have to do first is to calculate. See how will I'm going to approach this thing. There is a charge, right? There is a potential. Perfect. So basically, I'll just do charge potential combination will give me electrical work done. If I get the electrical work done, I'll just write it, divide by SRT, S is known, R is and T are constant. Okay, I'll get gamma plus minus, as simple as that. Okay, but it's not so simple anyway, we'll see. Now what, first thing first, I have to then figure out what is the RT. RT is a constant, okay, for a species. Now how to calculate RT, okay. Now, again, how is the ionic atmosphere? Remember, it is actually spherical symmetric, okay. Now, in electrostatics, there is a concept of charge density. Why do we use charge density? If we have a continuous distribution of charge. Now this is this interesting thing which Debye and Buchel said. Think about it, there is a central charge I am saying which is discrete, but with respect to that, all other ions, since they are moving around, this ion is seen as if it's a continuous distribution of a charge cloud. Where in the charge cloud, if first it is sodium chloride, I have basically the charge cloud's charge is -1. Just like you talk about at the very beginning when you talk about like hydrogen atom. Okay, there is one nucleus sitting and there is a diffuse electron cloud. Okay, but with respect to some other charge, this ion which I just said as a discrete, that is also moving. Okay, so there is a continuous charge distribution as if around this particular charge. Okay, so we can actually write in terms of the charge densities. Okay, and usually we wrote the charge density as rho. Okay, now so then basically there is a relationship between that potential and the charge density. Okay. Now if I can find the relation, and this is a standard relation, and that is known as anyone Poisson's relation. Okay. Poisson relation. There are many Poisson equations. Okay. So there are also Poisson equation for probably for diffusion. Okay. I don't remember. Yeah, it's basically vector calculus. Okay. And it basically says that if I take the del square of this phi, okay, I should get negative of charge density divided by the permittivity. This we are just taking as it is. I'm not going to derive this thing, of course, okay, because it is a lot of discussion. Now, what is this form of the del square? Del square already I know. Del square is what? Hydrogen atom problem. Okay. Del 2 del x2 plus del 2 del y2 del 2 del z2. Right? But looking at the symmetry of the problem, it's a charge surrounded by this thing. I should better actually use the spherical polar version. Okay. What is the spherical polar version? R square del scalar. Okay. This is R. Yeah, it's probably 1 by r, right? 1 by r square, first term. And then I'll have 1 by r square sine theta. Okay, del a theta, and then I'll have a it was r square sine square theta, that thing, right? But again, why I'm writing it? Because it is spherically symmetric. So theta phi part, I'm assuming that they are not changing. So now I'm in a better position in the sense that, okay, fine, this is only consists of this thing. Okay. And instead of partial derivative, I can write it as ddr because r is the only variable. Okay. Now I have basically the form of del square. I have to write it, act it on phi. Which phi? Basically that c1 by r e to the power minus r by r0. Okay. rd. If I do it and connect it to rho, then I will get a relationship between rho and rd, the divisor. Clear? Okay. Alright. So let us do that. Okay, let's basically try to work this out. So I'm going to basically take the del square of phi I. Okay, but before doing that, so del square of phi I is nothing but we just saw that it is 1 by r squared. Okay, I'm writing ddr because I don't need to write del. There is no theta and phi dependence. Okay, and I have here r squared ddr. Right? R squared ddr. Yeah. I can right now write phi here, but let us not do it. Let us first actually simplify this thing itself. Okay. We can do it in any way you want. So I'll have basically 1 by r squared ddr of this. Okay. So I'll have basically 2r. Okay. ddr. And then basically the first function, second function, differentiation, chain rule, right? So I'll have basically r squared d2 dr2, right? So basically I'll have two terms. One will be 2 by r, right? ddr, and the second term will be d2 dr2. Okay. On phi, basically. Okay. Phi has a form which has basically two r parts. One is 1 over r, one is basically e to the power minus r by r0. Okay, so let us do it. Okay, so let us first calculate this thing, ddr of phi I. Okay, which is basically ddr of some constant e to the power minus r by rd divided by r. Clear? Okay. Again, chain rule. Just take out the c first. Okay, e to the power minus r by rd, different, and there is also 1 by r. Okay, first function is say e to the power minus r by rd. Okay, so what I have e to the power minus r by rd, e to the power mx, derivative is 1 over m e to the power mx, right? So that 1 over m is basically times I will have minus 1 over 1 by rd. So it will be minus rd. Clear? Okay. Now differentiate the second function. Second function was what? like 1 by r basically. Okay. So the first function was e to the power r by rt. Second function, if I differentiate, it will be minus 1 over r square. Well, minus. Clear? Just simple chain rule of differentiation. Okay. Now I can leave it and then take the second derivative, but I'll actually play a trick. I'll actually write again phi back, because phi is hiding here, right? How? Basically c times this divided by r is phi. Okay. So this guy, just look at it. C times this divided by r is the phi. So the first term is nothing but minus RT into phi I. Right? Second term is C times this, then this. Second term is basically minus phi I by R. Clear? I didn't remember. Yeah. Correct? I think it's correct. I'm just taking the one. Yeah.
But like there will be 1 by r.
What?
Differentiation of e to the power of minus r by r will be minus 1 by r. Differentiation of e to the power minus r by r.
It will be minus 1 over r. This one, right? That will be minus 1 over r. This is correct, right?
Yes.
This is 1 minus r by r. Now the second thing, basically what I will do is that the chain rule, basically you just use d2 dr2, okay, of phi I, which is basically ddr of phi I, but ddr of phi I you have already computed, okay, and then you proceed with this thing. Okay, I'm not just leaving this. That will do it. Okay, so I will have ddr, I will have d2 dr2. Now you put back in this equation. Okay, so with ddr you have to multiply 2 by r, d2 dr2 you have to just the term. Okay, and then you add it. Okay, you could actually do it just simply like the full thing, but that will just reduce the number of steps. Okay, so if you do it, you will see that it will just reduce the very compact relationship, where you will get like rd square. Okay, how I will get rd square? You will get another rd pulling down. Okay, here, so you get basically 1 rd square. So you will get rd square and is equal to epsilon phi by r. Just using the notation. Just check this thing, okay, because most of the terms will cancel. I mean, there will be 4 terms, okay, and then 2 of them will cancel with each other. Not 4 actually, there will be more terms. Okay. Now, so this is basically a relationship of the RT square with the charge density. Okay, and there is also this potential, but that potential I wrote it like that. Okay, so what I did is basically using Poisson's equation. Okay, for a spherically averaged charge density. Okay, I established a relationship or definition. What do you mean by the divided? Clear? Okay, but still. Okay, I have to do a lot more things because I do not know what are the rho and this thing, right? So that I have to work out. Okay, yet. Alright. So this will be useful. I mean, like in the next step, actually, I will be going to use it. So basically, I can actually keep it somewhere here. All the results actually you could write here. So I got rd square is minus epsilon phi I divided by rho I. Okay, we'll be using that thing shortly.